Alright, so the final part of differentiation is this thing called kinematics. Now, kinematics describes the motion in a straight line. So, kinematics normally just describes the motion of an object, but all we need to know is how to use it in a straight line. So if we think about it, we can represent something as a straight line like that. Now we call the origin O, so that is the origin, and then you can go to the positive direction from the origin, or you could go to the negative direction, like so. Now displacement is something that we can measure. So if we consider a particle, as they call it, at O, so let's draw this in red. So this is a particle, and let's say it goes to 3. Well, the displacement would then be the length of this, almost. So it would be 3. So the displacement here, or S, we normally denote displacement with the letter S. So displacement equals S. In this case, it's 3. Because the distance that that particle has moved, so this is where it will be, is 3. So you might be wondering, what is the difference between displacement and distance? Because obviously if a particle moves 3 meters or whatever, that's also the distance. Well, the difference is that displacement can also be negative. So if we go in the opposite direction to -5, where this is -5, the displacement of the second point would be -5, but the distance would be 5 still, because distance can't be negative, but displacement can. And we call, because it can be negative, or because the direction matters, we say displacement is a vector quantity, like so. Right. So yeah, displacement is just measured from the origin point. So yeah. Right. So what we can do is, here is an example. The displacement can normally be given as a function of t. So the displacement is measured a certain time. So it says the displacement s meters of a particle from a fixed point O after t seconds is given by s equals 3t to the 4 minus 2t cubed minus 4. Find the displacement at the start of the particle's journey. So let's do that first. Right. Okay, so what we need to realize is basically this is a function. So this is, you could write it as st, like that, for example. So basically what that means is you could put in any time and you'd always get the displacement at that time. So right now we want to find it at the start of the journey. So at start, the time is equal to 0 because it's the beginning. So let's substitute that into the formula we have. So we have s3 to the 0 to the 4 minus 2 0 to the 3 minus 4, like so. And obviously these two go to 0, and we just get minus 4 meters. Alright. And then it asks, what is the distance between the particle and the point O after 2 seconds? So remember, the distance between the particle and point O, that is just the displacement. So the displacement is the distance, or as in we can get it from the displacement. So after 2 seconds, let's figure out what that is. So now t is equal to 2, right? So we substitute 2 into here, like so. Okay, and then what we do is that goes 2 to the 4 is 16, and 2 to the 3 is 8. And if you calculate all of that, we get 28 meters. Now, what we actually did was find the displacement, right? But remember, it asks for the distance. So if this was a negative value, we'd have to convert it into a positive value. So for example, if it asks for the distance for this question, for this answer, we'd have to give 4 meters. That's the distance, because the distance can't be negative. Alright, now let's talk about velocity. Now velocity is also a vector quantity, which means it can be negative. Let's consider this equation. Speed equals distance over time. Speed is measured in meters per second, and distance is in meters, time is in seconds. Okay? Now, this is not a vector quantity. We call it a scalar quantity, which means it can't be negative. So your speed also can't be negative. But now, let's consider this new equation. Velocity equals displacement over time. Same units, but the difference is, because displacement is a vector quantity, it can be negative. So the velocity can also be negative. So if you have a negative speed, if your displacement is negative. So if your speed is how also the rate of change of distance. So the velocity will be the rate of change of displacement. Velocity is rate of change of displacement, because it's displacement over time. So for example, if you were going in a negative direction, you'd have negative velocity. So if you were going if you were going in this direction, if you're going in that direction at a speed of 6 meters per second, you'd have a velocity of minus 6 meters per second, because you're going in a negative direction. If this is the positive and that's the negative, like that. And one other important thing to note is the object or particle is stationary, so it's not moving when velocity, we can denote velocity as v if we wanted to, equals 0. So that, if you think about that, when the velocity is 0, it means that the object doesn't have any speed, or it doesn't have any, it's not traveling any displacement, it's not displacing anything. So when the velocity is 0, the object will be stationary or will not be moving. And same when the speed is 0. Alright, now finally, we have acceleration. Now, acceleration is defined as the velocity over time. So the velocity is in meters per second, time is in seconds. So acceleration is meters per second squared. Now, acceleration, in fact, let me put these two equations in boxes. Second. There we go. Okay, so now what we can do is we can observe this in the same way and say, well, acceleration is the velocity over time, so the acceleration must be the rate of change of velocity. So, and it might be quite difficult to wrap your head around this initially. Basically, it means when the acceleration is positive, the velocity is increasing. And if the acceleration, so if acceleration or A is positive, velocity is increasing. If acceleration is negative, the velocity is decreasing. And if acceleration is equal to 0, velocity is constant. But when acceleration is 0, the object is still moving. It's just not picking up any velocity or losing any velocity, or picking up any speed or losing any speed. It's just staying at the same velocity. Right. So now we can use these three values, displacement, velocity, and acceleration, and we can link them all together. Also, just a side note, this here is called accelerating. I'll put it here. This is accelerating. This is decelerating. So, right. So, if we move over here, we'll see that we know that the velocity is the rate of change of displacement, and we also know that acceleration is the rate of change of velocity. So we can use these definitions. If you remember back when we were learning about differentiation, we can actually link these together if you remember what the rate of change of means. So to get if you want to get from displacement from velocity to acceleration, or S to V to A, what you want to do is you want to differentiate, because remember, if it's the velocity is the rate of change of displacement, so that's the same as saying it's the derivative of the displacement. And we know that the acceleration is the rate of change of velocity, so that's the same as saying it's the derivative of the velocity. So all you need to do is differentiate to get. So you differentiate once, to get from the displacement to the velocity, and then differentiate again if you want to get to the acceleration. Okay, now let's do a few examples. Okay. Now, this isn't as wordy as the other example, but it does mean the same thing. I just haven't written the same thing down again. So we are still talking, for all these examples, we're talking about the displacement in s meters of a particle from a fixed point O after t seconds, and that's the expression. Imagine this is written down for all of these questions. Now we have this as a function. Now we want to find the expression for the velocity. So let's do that. Now remember, we don't have the velocity here, but we can find it by differentiating. Because we know if we differentiate displacement, because velocity is the rate of change of displacement, we'll get velocity. So let's find ds over dt. Well, we bring if you remember, we bring the power down, so we get 3t, and then we take 1 off the power, so we get 3t squared. Similarly here, we get 2t. And remember, if you only have the power to 1, we just get rid of the t, and it just becomes a 1. Now, so this is the expression for the velocity, because this is v. V is the derivative of s. If you want, we can write it out like so. Now, it says find the velocity at t equals 4. So, what we can do is we can use this equation that we've just calculated and substitute 4 inside it. So, 4 squared will be 16. That will be 8 plus 1. And that will equal 33 meters per second. Okay. Now again, imagine all of that writing was still here for this next example. So now we have this new equation which denotes the displacement. And now it says find the expression for the acceleration. Okay. Well, let's do the same thing. We can figure out the velocity by differentiating this function. So again, let's bring the power down, take 1 off the power, bring that power down, take away the t here. Remember, constants just disappear. We differentiate. Okay, so now we have the velocity, but how do we get to the acceleration? Well, if you remember, we can just do the same thing. So we can differentiate once to get to the velocity, and differentiate again to get to the acceleration. Let's differentiate this to get the acceleration. This new equation here, or expression. So let's bring the power down again, so we get 12t, and then the t disappears here, and this constant disappears. This is the expression for A. Right. So now B says find the acceleration at t equals 2.5. So again, let's substitute 2.5 into here. And we will get minus 6 meters per second squared, because remember, the acceleration can be negative because it's a vector quantity, and so it's decelerating. You could also potentially get a question that gives you the acceleration, so it could say A equals minus 6 at what time? And then you just substitute minus 6 into here. And then it's just the opposite process. So you add 36 to both sides, divide by 12, and you should get t equals t.5. So just bear in mind that it can work both ways. Okay, let's look at the final example here. And it says this is the equation we're given, and S is in meters. It says find the initial distance from point O. So initial basically just means at the start. So again, we can substitute 0 into here, and we'll get minus 5 meters, like so. Find an expression for velocity in terms of t. Okay. So again, we can differentiate to get velocity. ds over dt. Okay, and then we have 6t squared minus 2t. Like that. So that is our expression. But now it says find times when particle is instantaneously at rest. So instantaneously means just at one point in time. So like at a given point in time, when is it at rest? So what we can do here is remember when an object is at rest, or another word for this is stationary. Remember we said that that's when v equals 0. So let's substitute v equals 0. So this is the equation we have. So let's substitute v equals 0. Now it wants to know the times when it's at rest. And remember, it says times, so it's looking for more than 1. Now, we can see that we've got a quadratic here. So we can factorize this. So first off, we can take out a common factor of 2t, because they both have 2t. So if we divide this by 2t, we get 3t. And if we divide this by 2t, we get 1. Like so. And now that we have these two, we can say, okay, what are the values of t that will make it 0? So let's focus on 2t. So when 2t equals 0, when t equals 0, right? Because when t is 0, this whole thing here will be 0. And 3t minus 1 equals 0 when t equals, well, we can move the 1 over to get 3t equals 1, and then we'll get t equals a third if we divide 3 by 3. So these are our two times. So these are the times where it's instantaneously at rest, or when v equals 0. Yeah, so for this, you just have to imagine it to, because we don't have a constant here, this is what a factorized quadratic looks like. Okay,